Thank you very much. First of all, to all of you for being here, to the organizers for organizing this very nice workshop and inviting me, and Damir for the introduction. So, between the two topics of this conference, I'm only on the algebraic combinatoric side. There will be no integrability in this talk, but if you see any connections, of course, I'm always very happy to discuss this with you. So it will be between two topics. One of them is the theory of integer partitions and partition identities from the combinatorial point of view. And the other one is commutative algebra. And we will see that a very classical partition identity, the Andrews-Gordon identities, can be related to certain ideals in a particular ring that we will define later. Okay, so I will start by presenting the identities. Then we will see the connection with commutative algebra, which will lead to a conjecture. And in the last part of the talk, we will prove that conjecture. Okay, so let's just recall quickly, mostly for notations, because we have seen many partitions already. But a partition of non-negative integer n is a non-increasing sequence of positive integers, which are called the parts, whose sum is n. And n is called the weight of the partition, and we will denote it between vertical bars. And the number of parts is the length of the partition. So here I listed all the partitions of 5, and partitions correspond to Young diagrams, which I have written here. So I know earlier in this workshop, many people filled the Young diagrams with some values to get standard Young tableaus, etc. I'm not going to fill them. They are going to stay all blank like that. But you will see there will still be colors on them, and certain things will happen nonetheless. So is this not? I always forget which is called what, but yeah, no, the largest part is on top. Yeah, so that's English notation, or yeah, okay, English notation indeed. Yeah, okay. So the Rogers-Ramanujan identities are were originally Q-series identities, which we will see in a few slides, but I start by presenting them combinatorially. So they say that you take a parameter I, which is either 1 or 2, and then for any non-negative integer n, there are as many partitions of n such that the difference between consecutive parts is at least 2, and that the part 1 appears at most I minus 1 times, so either 1 time or 0 times at most, depending on the value of I. So this is the same as the number of partitions of n in two parts, not congruent to 0 or plus or minus I mod 5. So usually it's stated by saying congruent to plus or minus 1 modulo 5, for example, but for the generalization, it's nicer to write it in that way. Okay, so if we take, again, our partitions of 5, if we take the partitions that have difference at least 2 between consecutive parts, and where 1 is allowed, we have 2 partitions, these 2. And indeed, we see that we also have 2 partitions into parts congruent to 1 or 4 modulo 5. And same for the case where you don't allow the part 1, you have only 1 partition, which is 5. And you also have 1 partition only into parts congruent to 3 or 2 modulo 5. Okay, so these partition identities, they appear in many different fields of mathematics. Of course, combinatorics might be the most obvious, but they also appear in statistical mechanics, so that can interest a few of you. So that was, it was proved by Baxter that there is a connection to the hard hexagon model, for those who are interested in that. There is also a connection to number theory, which will be more obvious when we see the analytical form of this identity, but it's related to modular forms and this type of things. It's also connected to the representation theory of affine Lie algebras. So you can interpret both sides of the identities as different ways to write characters of certain Lie algebra representations. And there will be also a few connections with algebraic geometry and commutative algebra, which we will see a bit in this talk. Okay, so they appear in really many places. Okay, so to see the analytic version of these identities, I will just recall quickly a few things about partition generating functions. So the Q-Pochhammer symbol, you have already seen it. So let me just recall the principle of how you compute the generating function of partitions into distinct parts. So if the power of Q counts the number that is partitioned, and the power of Z counts the number of parts, the generating function for partitions into distinct parts can be written that way, by choosing for each positive integer whether it appears in the partition, which will be equivalent to picking the term that is not equal to 1 in each of these products, or if it doesn't appear, which would be equivalent to picking the 1. So if you expand, you get all possibilities, and hence all partitions into distinct parts. So if you take partitions into, partitions that do not have the condition that the parts need to be distinct, you take the same principle, you take the product over all positive integers, and now each part you can not take it at all, or take it once, or take it twice, etc., etc. Okay, so this is quite classical, but you can also do the same thing by taking the product not over all positive integers, but over a subset of the integers. So for example, in the Rogers-Ramanujan identity, we were interested in partitions into parts congruent to 1 or 4 modulo 5, for example. So to get the generating function for these partitions, you do the same principle, but instead of multiplying over all n, you multiply only over n congruent to 1 modulo 5, and you get the same principle. Also, in the same way, if you want to put an upper bound on the size of the parts that are allowed, you do the same, except you take a finite product, so you will get a finite Q-Pochhammer symbol. So, to sum up, these things also can be written very nicely in terms of Q-Pochhammer symbols. So if you want to take the generating function for partitions into parts congruent to k modulo n, you can write this very simply, and you can read the congruence conditions on the Q-Pochhammer symbol, because you get qk, qn, infinity. So this one is the generating function for partitions into parts at most k. But it's also the generating function for partitions into at most k parts, because you can rotate the Young diagram of a partition by 90 degrees, and the number of parts will become the largest part, and vice versa. Okay, so now we can rewrite the Rogers-Ramanujan identities in terms of their generating functions. So this will be the generating function for partitions into parts congruent to 1 or 4 modulo 5, which is the same as not congruent to 0, 2, or 3 modulo 5. For the generalization later, yeah, it's still nicer to say it that way. And this one is for 2 or 3 modulo 5. Okay, so for the left-hand side, we will see on the next slide. So we wanted partitions where the difference between consecutive parts is at least 2. So to do that, the idea is to start with a staircase of size with k parts. So the staircase 1, 3, 5, etc., which has difference exactly 2 between consecutive parts. And to this, you will add a partition which is in at most k parts. So the staircase is generated by q to the k squared. The partition into at most k parts is generated by 1 over q qk, as we saw on the last slide. So to add them, it's very simple. You add the first part of this partition to the first part of the staircase, the second to the second, etc., etc. And you always get a partition because you didn't have more than k parts here. And the difference between consecutive parts will now be at least 2 and not exactly 2. So if you had two parts here that were equal, then they will still differ by exactly 2. But for example, here we don't have a third part, so in the partition we obtain here, we have difference more than 2. Okay, so we can do the same for the other Rogers-Ramanujan identity. The idea is almost the same, except we will start, now we don't want 1 to be allowed as a part anymore. So instead of this staircase, we will start with the staircase 2, 4, 6, etc., which already doesn't contain a 1 and has a difference at least 2. So if you add a partition to that, you will get a partition with difference at least 2 and with 1 forbidden, which is exactly what we want. Okay, so these are the combinatorics of the Rogers-Ramanujan identities. So there is a generalization which is due to Gordon, and which now has two parameters, r and I, and I is between 1 and r. And now you don't have difference 2 between consecutive parts, but between parts that are at distance j plus r minus 1. So when r equals 2, this is equal to, it's the same as consecutive parts, but when r is bigger, it's different. And we also don't want the part 1 to appear more than I times. And on the other hand, we have ERI, which is a set of partitions into parts not congruent. That's why I shouldn't say it wrong now after changing the previous identity because of that. So into parts not congruent to 0 or plus or minus 1 modulo 2r plus 1. And again, for all n, the partitions of n of these two sets are equinumerous. So the Rogers-Ramanujan identities, as I said, correspond to r equals 2, with the two possible values of I. And again, there is also an analytic version of these identities called the Andrews-Gordon identities. So these formulas were proven by Andrews. And so it's not completely obvious that the left-hand side is a generating function for the partitions with difference conditions. But the right-hand side, at least, you can recognize still that this is, so on the denominator, you have all partitions. And on the numerator, you divide, if you want, by the generating function for partitions into parts congruent to 0, I, or minus 1 modulo 2r plus 1. So you are left with partitions into parts not congruent to these numbers. Okay, so same thing here. If we set r equals 2 in this identity, we will recover the Rogers-Ramanujan identities. Okay, so there are always these two versions of the identities. And now we will see a combinatorial interpretation, a different one, because of course we have already seen one, but one that is a bit more natural, with this generating series. So the Q binomial coefficients are defined as follows. So there are quotients of Q Pochhammer symbols, and equal to 0 if k is negative or strictly bigger than n. And they are the generating function for partitions whose Young diagram fits inside a box of size k times n minus k. So the Rogers-Ramanujan generating functions here can be rewritten in terms of Q binomial coefficients in the following way. And this will be nicer to interpret combinatorially and draw nice pictures. So let me draw a little bit on the blackboard. So if we take a partition, the Durfee square will be the largest square that fits in the top left corner of this partition. So here, let's say it would be something like that. And for the interpretation of this identity, we will need also some other quantity, which is a vertical Durfee rectangle. So it's pretty much the same principle, except now you want to find the largest n times n plus 1 rectangle that fits in the same picture. So here it would be, I don't know, something like that. Okay. So, and if you have, and if this is the Durfee square, that means you don't have any box here. Otherwise, you could have extended it. And same thing, if the Durfee rectangle is here, that means you cannot have any box here. Otherwise, you could have extended it as well. Okay. So now let's see how we how we can use this to find the interpretation of Andrews-Gordon. So okay, let's say we start with a square. So we start with my red square here. Then what is below it is still a partition. So now this partition, we can also find its Durfee square or rectangle, or that depends on us. So let's say the Durfee square should be something like this, the second Durfee square, I mean. Okay? And then you can continue as many times as you want until you exceed the partition. Okay. So this is more nicely done here. So here we have done that by taking first two squares, A1 and A2, and then two rectangles. So in my notations, in all over the talk, whenever we have rectangles, I will always put a prime on the notation, because sometimes when the drawing is bigger, it's hard to see what is a square, what is a rectangle. Okay, so here you have a Durfee dissection with two squares and two rectangles. And the interpretations of the Rogers-Ramanujan, the Andrews-Gordon identities, is that when you do this Durfee dissection, if you do first, first you do I minus 1 squares. So here I minus 1 would be 2. And then you do only vertical rectangles. Then it should be that starting from the half rectangle, everything is empty. So we take the convention that below this A prime 4, there is still some empty, infinitely many, if you want, empty rectangles. And there is another condition. It is that for all these rectangles, the last part of the rectangle must be exactly a part of the partition. So you cannot have anything here where I put a little cross. Okay, so this is the interpretation of Andrews-Gordon. So why is that? So first of all, the exponent of the q in the numerator, you have all the sizes of the squares or rectangles that are squared, and then for those which are rectangles, you still add this line in addition. And mu1 here is a partition into at most n1 parts, so we get here the denominator here. And then for the following partitions mu I, you get a partition that fits in this box. So it's a box of size n minus 1 minus n2, sorry, n1 minus n2 times n2. So for example, that gives us this q binomial coefficient, and the other ones work exactly in the same way.
Sorry, I didn't understand the
yes?
ni plus r minus 1 in the exponent.
Yes, so if you forget about that first, you get all the squares, yes. And this one is just because after a while, starting from index I, you get rectangles, not squares, so you have to add the line, yes. Thank you for the question. Okay. Yeah, so is it clear for everyone?
Sorry.
Yes? No.
Why is the denominator q n1? Why is it just n1 and not the others?
It is n1 because the partition here on the right of your first Durfee square, it's not. It can be as long as you want. So it's only a partition into at most n1 parts. So it's generated by 1 over q n1. But these ones, they are bounded also on the right. Yeah, because otherwise, if you had something that goes up to here, let's say, that would not be a partition. Yeah. So the other ones, they are bounded. The first one is not. Okay, so this is how you get the connection. So this gives a different interpretation of the sum side of the Andrews-Gordon identities.
So this was not the original interpretation?
No, that was the one from Andrews, but the one from Gordon, no, it was with a difference between parts at distance r minus 1, that is at most 2. So that's quite different, and it's not so easy to see that it's the same. I mean, and it's not the same, but they are in bijection, I mean, yeah. But that's not an easy bijection. Okay. So, but this is not due to me, it's due to Andrews, yeah. Okay, so just remember, because we will have many letters in this talk, so ARI, that's the partitions that can be written in that form with parameters R and I. Okay, so now let's talk a bit about commutative algebra. We will see a connection. So first of all, we will consider the algebra of polynomials in over a field K of characteristic 0, in infinitely many variables that are indexed by the positive integers. And this algebra of polynomials, you can grade it by saying that the monomial xi will have weight I. And if you have a product of some xi k, then the product of this monomial will be the sum of the weight of all the variables that appear in it. And we do all this in the commutative case, so because I advertised commutative algebra, so we can always assume, we can always reorder the xi's. So we can assume that they are in non-increasing order. And then maybe you already see a connection with partitions, because then the indices I1, I2, etc. will form a partition. So our ring, our algebra of polynomial R can be written as the direct sum of Rn, where Rn is the vector space generated by the monomials of total weight n. And as I just said, there is a very simple correspondence between monomials and partitions by just taking the indices in non-increasing order. So now there is the Hilbert Poincaré series of R, which is the generating function of the dimensions of those spaces Rn. And because there is this correspondence, the partitions, or the monomials ordered in a nice way, form a basis of Rn. So there will be as many, the dimension will be the number of partitions of n. And we already know the generating function for partitions. So for this general algebra R, the Hilbert Poincaré series is relatively simple to compute. But now we don't always want to study the general R, right? Maybe we want some additional conditions. So that's what we will do now. So let's consider an ideal in this in our algebra R, which will be generated by the squares of all the xk's and also all the xk plus 1 for all k. And also, but it's a bit less important, x1 to the I. So we still have I which is equal to 1 or 2 at the moment. Later it will be something else. So now if we take all these polynomials and we quotient by this ideal, this will correspond to the Rogers-Ramanujan partitions with different conditions. So why? It's because, so initially you can have anything. But you remove all monomial / partitions where k appears twice. So that means parts cannot repeat. And you remove also all partitions or monomials where you have both k and k plus 1. So you cannot have consecutive parts either. So if you cannot have the same part or consecutive parts, that means you have difference at least 2. And the fact that we remove here x1 maybe can forbid the fact that you have 1 as a part. But again, this is a bit less important. So this tells us that if we take the Hilbert Poincaré series of this quotient now, so this is the same as the generating function for the Rogers-Ramanujan partitions, which we have also computed. And if we already know Rogers-Ramanujan, we can also write this as a product. But so far, I just wanted to make the connection between Rogers-Ramanujan and these ideals. Okay, so now, Bruschek, Murtada, and Scheppers, who are initially algebraic geometers, and we are working on arc spaces, which is a theory I know close to nothing about, so don't ask too much, please. They studied the quotient of R, not by this very simple ideal, but by a slightly more complicated one, which was related to their arc spaces, which is a differential ideal. So the idea is that you start with an element, x1 squared, and then you take all its derivative according to some rule. So the rule is that the derivative of xj is xj plus 1, and it satisfies the classical Leibniz rule of derivatives. So if you take x1 squared, you derive, you get 2x1, x2. You derive, you get 2x2 squared, sorry, plus 2x1, x3, etc., etc. And the terms become bigger and bigger. I only wrote the first few. And you take the ideal generated by all these polynomials. But now it's a bit more complicated, because here you had only monomials, but here you have polynomials. So you have several monomials, and you don't really know which one is the most important in some sense, between, for example, this x2 squared and this x1, x3. So this is where monomial orders come into play. So we will see two of them. First of all, there is the weighted lexicographic order. So if you want to compare two monomials, written like that, first you compare their weights. So that's why it's called weighted. So if one has a smaller weight, then it's smaller than the other one. Now, if they have the same weight, that's where the lexicographic part comes into play. So you look at the first index for which they differ. So assuming this index is I, you compare the powers of xi on both sides. And if the one, if ai is smaller than bi, then the first monomial will be smaller than the second. So in our case, the smallest monomial in a polynomial will be called the leading monomial. And here, for example, if we take this one, the first term where these two monomials differ is already for x1. First, they have the same weight. Okay, I didn't check, but here they all have the same weight. So, okay. So, and for x1, here you have here you have x1 to the power of 1. Here you have x1 to the power of 0. So this one is bigger. And the same applies here. So for each of these polynomials, you pick the leading monomial. Now there is another order which will be important. It's a weighted reverse lexicographic order. So same, you first compare the weight, and then you look now at the last. You start from the end, and you look at the last xi for which there is a difference between the two. And now it will be the reverse lexicographic order. So if the power ai is bigger than the power bi, then this monomial is smaller than this monomial. So here same. So from the right, the first time it differs is at x3, because here you have some x3, here you don't. But here you have x3 to the power 0, here you have x3 to the power 1. This power is smaller than that one, so in reverse order, this is a leading monomial. So you can see that if we take different orders, it might not be the same leading monomial that we pick in our ideal. Okay, so these authors that I just mentioned, Bruchek, Murtada, and Scheppers, they proved that the leading ideal of this differential ideal, where again we do something for x1, but I will not insist on that, it's not the most important. So this differential ideal, if you take the ideal generated by the leading monomials with the weighted reverse lexicographic order, so the second order I just defined, then it is exactly the same as the simple ideal that we studied before, that we saw that it's exactly in correspondence with Rogers-Ramanujan partitions. So thanks to that, also with this differential ideal, the Hilbert-Poincaré series will also be the Rogers-Ramanujan generating functions. But this is a bit a lucky situation, because usually this very simple ideal, J0, that we like, it's usually, if you take any order, it's usually not going to be generated by the leading monomials of your differential ideal. If it is, it means that the system of generated is called the Gröbner basis. And so if you pick different orders, you may have different Gröbner basis or not have a Gröbner basis at all, like you can have many situations. And we can wonder what would happen if we take the weighted lexicographic order instead, right? It might seem more natural. It's well, maybe even more simple. You don't have to reverse things in your head, but you will see it's actually more complicated. But yes, so and that will lead to this conjecture. Okay, so let's go back at Gordon's identities that we already saw. And actually, Bruchek, Murtada, and Shepers, they studied also the Andrews-Gordon identities. They generalized their idea of what we just saw on Rogers-Ramanujan. So if you take the differential ideal, but starting with x1 to the r, and not to the 2 only, then also with the weighted lexicographic order, everything works fine. And the leading ideal is also something quite simple, with only monomials, that we can see, but I will not do the details, is in correspondence with these conditions. It works the same way as Rogers-Ramanujan, just a tiny bit more parameters, but very same idea. So I hope you trust me. And Afsharijoo, who was a student of Hussein Murtada, one of these 3 authors that I just mentioned, she tried to study the weighted the weighted lexicographic order, not reversed. And she managed to guess the leading ideal under that order, but actually it's not easy at all, and it's extremely hard to prove that it's actually a Grobner basis, because it's not differentially finite, so that means you cannot get it from derivatives starting from a finite number of polynomials. So it's complicated. And that led her to find a conjecture, which was that, the conjecture basically is that the set that she guessed is indeed a Grobner basis, but this is equivalent to a conjecture on partitions, if you want. So she defined these we will see that in a second on the blackboard. So she defined complicated quantities here on partitions, and she said that the partitions satisfying some conditions on these quantities are equinumerous with the Andrews-Gordon partitions. Because if it is indeed a Grobner basis, we already knew the Grobner basis according to this other order, and we knew that was Andrews-Gordon. So if this is also a Grobner basis, you should get Andrews-Gordon again. Okay, so for this one, I will also do a quick picture. Okay. Or maybe I shouldn't do something too big in the bottom. Okay, so this PIM. So here again we have r, which is a positive integer, and I is less than r. So far I will not mention I anymore. So when m equals 1, we have P1, which is just the smallest part, lambda L. So the last part of the partition. So this thing is P1 of lambda, but I also don't run the lambda. Okay, so then to get P2, you take lambda with index L, which is the length. So okay, so this is L. L minus, here we just have one term in the sum, and it's this P1. So what I will do is that I will do a square of side P1. So this will also be P1. And so the P2 will be the part just above. Okay? And now, P3, it's the same thing. You start with this part, and you take lambda, the part with index L, so we start here, minus P1, we go here, minus P2. Well, if we do a square again, we go there, okay? So here that would be P3, etc., etc. And so this is up to Pi. Now, starting at Pi plus 1, small difference, the plus m minus I here means that instead of doing a square, you will do a rectangle, but of height 1 less than the length. Okay, so for example, then let's say I is 2, so now we start with rectangles. So here you take a rectangle of size P3 minus 1. Okay, and here we exited the partition. That can happen, it's fine. It could be that it still continues if we didn't exit, but when we exit, we stop. And what she says here, basically, is that she considers partitions where either you can draw less than r minus 1 squares or rectangles, or if you draw exactly r minus 1, then this condition tells us that the sum of the PIs that I just drew minus here accounts for the fact that you have some that are rectangles, so some of them have height 1 less. That should be more than L. So, and L was the total height here. So for example, here we have 3 squares / rectangles, and indeed the size is more than L, because you end up higher than the partition. Okay, so she purely phrased it combinatorially, not combinatorially, sorry, just with these formulas, and that was already part of the work to find this dissection. Okay, so yeah, we proved with several colleagues that this conjecture is true. And to do this, we defined even a few more sets of partitions. So the one that was originally in the conjecture, we call that CRI. So we define 2 new sets. So this one that I just described will be called BRI. We will see. And there will be one last that is called DRI. And we will show that all these sets are actually equinumerous. And even more surprisingly, BRI that I just described and DRI, which I will soon introduce, they are even exactly the same. It's not just that they are in bijection, but they will be the same. And they will give rise to yet another type of dissection.
Sorry, but this construction that you have, isn't that the same that Andrews had?
No.
Coordinated?
No, Andrews was starting, so Andrews is still here, for example, so it's the red one. So you start with a Durfee square. So inside the partition, you start from the top. You start with squares. And so here you start from the bottom, okay, also with squares. But here you start here, and you always stay inside the partition, whereas here you start from the bottom, and you can go outside. And here the rectangles were vertical, and here they are horizontal. And you will see that in the DRI, we will also have horizontal rectangles, but it will look more like what Andrews did. Okay, and finally we show that 2 things have the same generating functions. Okay, so actually I took a bit of advance in what I wanted to show, but whatever. So this is this is the interpretation of the conjecture of Afsharijoo. And so I will just also write it in my slide. So we will call these squares, they didn't have names yet, so we will call them bottom squares because we start from the bottom. So the bottom square is exactly the square of side P1 that I said is here. So you take the smallest part and you draw a square starting from it. Bottom rectangle is similar idea, except you take a horizontal rectangle with 1 less than the width. And it's the same thing. You can, as I showed here, if you first draw the first bottom square, then what is above is again a partition. You take again the bottom square, etc. So you get a dissection in the same way as similar way to Andrews, but with the differences that you just made me state. And we will call BRI the partitions, such that if you first do I-1 squares followed by rectangles, then whatever is above the R-1 rectangle is empty. Okay, so here we would have R-1 equals 4, because above this big rectangle, there is nothing, okay? And so we constructed it thanks to the definition of the conjecture. So by definition, this set BRI is just a combinatorial way to express the set CRI of the conjecture. Okay, so now we will see that it actually corresponds to something else. Yet another dissection. So this will be the horizontal Durfee dissection. It's also new, but it will be more similar to Andrews. So you start by drawing a horizontal Durfee rectangle. So let's say in this partition, it should be. Yes, I still have other colors. So in this partition, it would be this rectangle, okay? So, and here you shouldn't have anything here. Okay, so just the length here is one more than the length there. And again, you can continue, same thing, just like for the classical Durfee dissection. And here, the condition is that you will first have r minus I rectangles, and then you will have squares, okay? So we call di the set of partitions such that in this dissection, all the squares below the r minus 1, again, are empty. And that's a bit, so here you can still use similar reasoning to what I did for the Andrews dissection to find a nice expression for the generating function. So it's a very same idea, except here you just have d1 minus 1 because the height is one less, but then the q-binomial coefficients, they work in the same way. So I will not give details again, but you get this expression. So at least this generating function is okay to compute. The one for the bi's is a bit more complicated because the problem is you can exceed the partition. So it's harder to count, so you would have one more sum for all the possible heights by which you exceed. It's not that simple if you don't see the connection with DRI, sorry. Okay, and in that paper, the same paper, we proved that for all R and I, BRI, so the partitions where you exit after R minus 1 bottom square / rectangles, is the same as DRI that we just saw. So here is an example on the same partition. Indeed, you have four squares or rectangles on the left and 4 on the right. But it could be a coincidence, right? We don't know. So let me just give you a quick idea. When you take the case of only squares, so when I is it 1 or R? I don't remember, but the case of only squares. Well, so in blue, I put the bottom dissection, in red, the Durfee dissection. And you can see that if you look the height at which the squares stop and start, they are interlaced. Like, so initially they coincide if you start from the bottom. But here, so this is so the second height of a Durfee square is between the first and second height of the bottom squares. And that's always true. You see, if you go from bottom to top, you see a black line, blue line, black line, blue line, etc. And actually, this is a key ingredient in the proof, that you get this interlacing, because then it will mean that you have the same number of squares of the two types. Of course, it's a bit simplified, but that's the idea. So yeah, here I'm just writing the same thing more formally, but this is what I just explained. So if you write the heights respectively HJB and HJD, depending on whether it's a bottom dissection or Durfee dissection, then you have this interlacing property. And so the case of only squares is the simplest. You have the case of only rectangles, which is also relatively simple. And the general case where you have first squares and then rectangles is a bit more tricky, but you can still prove it in a similar technique. But I will hide the difficulties for this talk. But yeah, if you want more detail later, I can provide. And so we prove in that way that BRI and DRI are the same thing. So remember, we had found a nice formula for the generating function for DRI, because again, it was just the dissection with like these yellow rectangles, and it was all inside the partition, so you don't have this annoying property that it goes out. And we had those q-binomial coefficients in the dissection, so we had a formula before. And in that formula, you can have cancellations in the binomial coefficients, a bit like for Andrews-Gordon, actually. And most of it cancels, except that you are left with one little term here that is different from Andrews-Gordon. And also, here on top, you get some minus something, contrarily to Andrews-Gordon when you had plus. So you had plus in Andrews-Gordon because you had to add the. So sorry, if you had a vertical rectangle, so that was the square, and then you had to add this row. But now, if it is a horizontal rectangle, we see it more like being this square missing that row. So that's why we get the minuses. And then we wanted to, the last thing to do is to prove that this is equal to one of the many members we already know for the Andrews-Gordon identities. So either the sum that we saw before, with the pluses and without this thing, or the product. And strangely enough, you could think it's closer to the sum, but actually it's simpler to prove that it equals the product. So to do this, we changed the, we replaced I by R minus Y, which doesn't change much. And what we did was proving that this equals this product. To do that, we used a formula due to Bressou, which is the following. So he proved it completely analytically in 1980, apparently. And so you see it is not the exact same formula, but you also have the minuses here. And here you have a sum of products, so it's not exactly the same. But luckily for us, if I equals 0, well, this is just one product, right? So that's fine. And you don't have the minuses either, because you don't even enter that sum. So for 0, it will be just one product, and it's a generating function for DRR, so the case with only squares. So that's also clear that it's the same as Andrews-Gordon with only squares, because it doesn't matter that the rectangles are vertical or horizontal if there are no rectangles, right? So this case is fine. But then, if you get I that is non-zero, you can actually write the generating function for DRR minus I as the difference of two consecutive of these terms, which is very lucky because also here that was the sum. So if you do one minus the next, you get just one product. So you get the infinite product that we wanted. So the one from Andrews-Gordon. So that completes the proof of this theorem. So we saw that there are several very different types of Durfee or bottom or whatever dissections. So we have 3 different types of dissections now, and we have proved that in the end they give rise to the same identity, but only the one from Andrews was known initially. So it could be interesting to know if there is a bijection between at least the 2 more similar ones, right? So the 2 Durfee dissections, but either with horizontal, so first squares, then vertical rectangles, or the other one is first horizontal rectangles and then squares. But actually, it's not that simple. So when it's only squares, as we said, of course, it's clear because there are no rectangles and it's the same. If there are only rectangles, there is a simple bijection by rotating the rectangles. So if you have, well, maybe I do just a new picture. Okay, so let's say here you have a horizontal rectangle. Let's denote it that way. And the next one would be like that, or I don't know, like that maybe. Oop. And still whatever. The last one would be here. So if you just rotate this one by 90 degrees, you will get first this Durfee square, which will have this partition to its right, and below it you will have this part. And this part will now be on its own because we rotated, so there will be nothing to its right, which was exactly the condition in the dissection of Andrews. You needed the last part of each vertical rectangle to be a part of the partition. So, and then you continue doing it, you have no problem. But if you have both squares and rectangles, it's usually not that easy because you cannot just rotate anymore because it could be that then it creates objects that are not really partitions. We don't like that. So this one, so we were able to do the case where there is at most one rectangle, and it was already not so simple, like 2 pages. For more, we don't know. And it's quite strange because they seem similar, but actually when you try to do something on it, it's not that easy. Yeah. So finally, there is also another identity a bit similar to Andrews Gordon, which is due to Bressou, again, and which is an analog of the Andrews Gordon identities, but where now you have congruence conditions modulo 2R, and not 2R plus 1. And they work in many ways in a bit similarly because, for example, there is also a generating function a bit in the same shape. So one thing that could be interesting would be to see if we can also find a connection between Hilbert Poincaré series of ideals for this identity. And I've been working on this with Frédéric Jouet, who is one of my co-authors on this paper, and with my postdoc, Zafirakis Zafirakopoulos. And it's in progress, but it seems harder so far. Yeah, because it's not so clear again what is a Grosvenor basis, what is not. I mean, finding an ideal is fine, but a differential one that has a Grosvenor basis, that's the problem. And finally, if you're interested in this type of identities, very recently, so still with Frédéric Jouet and with my former postdoc Isaac Conan, we have found a bijection showing that I said it was not obvious that the combinatorial conditions of the combinatorial version of the identity correspond to this generating function. It was clear that it corresponded to the Durfee dissection, but not clear that it corresponded to the difference conditions between parts. And we have given a bijection between these two, between the difference conditions and objects that are clearly generated by this series, both in the case of Andrews Gordon and Bressou. In the case of Andrews Gordon, it's a different way to express a bijection that was due to Warner, but ours is a bit more general because it also works for Bressou and for many subsets of these sets of partitions. And that led us to find many partition identities of this type, including the one that we needed to prove this conjecture. So the one that the generating function for DRI is the infinite product. So that was it's one of the consequences of our bijection. So if you're interested in that, you can look on my web page or on the archive. And I will stop here, and thank you very much.